Our first lecture of week 2 will discuss Kirchhoff's voltage and current laws. This is from sections 2.4 and 2.5 of your textbook. And what we will do today is define these laws as well as use them to find voltage, current, and power in circuits and confirm that circuits obey the law of conservation of energy. First definition is a node. A node is a meeting point where two or more circuit elements meet. Kirchhoff's current law states that the algebraic sum of all the currents into or out of any node must equal 0. Another way of writing that is the sum of the currents in a node is equal to 0, or current in equals current out. In this top definition, if you look at our figure, we've made the current going into the node positive and the current coming out of the node negative. So you would have I1 minus I2 plus I3 plus I4 minus I5 equals 0, which is algebraically equivalent to the second equation, current in equals current out. Note that Kirchhoff and Ohm's law apply to phasors, but it's not necessary to convert the circuit to the frequency domain model of a circuit and use complex numbers. We will talk about phasors more at the end of the quarter. However, a lot of the laws that we discussed do apply to DC and sinusoidal steady-state circuits. A closed loop in a circuit is any closed path through selected basic circuit elements that returns to the original node without passing any intermediate node more than once. We've actually seen a closed loop in lecture 1-3. Kirchhoff's voltage law states that the algebraic sum of the voltages around any closed path in a circuit equals 0. Another way of stating this is the sum of the voltages around the loop is equal to 0. There are two ways to write this law. The first one is to say voltage rises equal voltage drops. So if you look at our circuit, since we've defined the current to be clockwise, V4 and V1 are the rises, and then we have voltage drops V5, V2, and V3. Another way of doing this is to make the rises negative and make the drops positive and sum them together to equal 0. Notice that these two equations are algebraically equivalent. We're going to show that we can use Kirchhoff's current law to confirm that the following circuit obeys the law of conservation of energy. Notice when you have a single node pair or a parallel circuit, we use KCL. And the first thing you do is you define the ground reference node, which we always use the bottom to do that. And we define a voltage for the top node, which I'll call Vx for voltage unknown. In order to do KCL, you have to make some assumptions. The first assumption we always make is that if the current is not given, it's leaving the node. So I'm going to show the current leaving through the 2 ohm resistor. It's already leaving for the 5 amp current source. I'll show the current leaving for the 6 ohm resistor, and the current's already coming in for the 10 amp source. So the KCL equation would be the current out through the 2 ohm plus the current out through the 5 amp plus the current out through the 6 ohm equals the current coming into that node through the 10 amp current source. Although this is a good equation, it's not very helpful. If we could solve for one equation and one unknown, that would be helpful. So the first thing we want to do is to describe the current through the 2 ohm resistor in terms of our variable voltage Vx. Based upon Ohm's law, the current through the 2 ohm resistor is Vx over 2. Notice we assume that Vx has a higher potential with respect to ground to make sure that our resistors are drawn to be voltage drops. Plus the current through the 5 amp current source is just 5. The current through the 6 ohm resistor is, that's right, Vx over 6, and that equals 10. So the good news now is that we have one equation and one unknown. So we can solve for the unknown node voltage Vx. Vx is equal to 7.5 volts. So now that we have that information, we can solve for every current in the circuit, and because they're in parallel, we know that they all have the same voltage. So let's make our law of conservation of energy table. The first column heading is the elements. The second two columns are the voltage and the current. And the last column is the power in watts. For the rows, I'll have the 10 amp current source, the 5 amp current source, a 2 ohm resistor, and the 6 ohm resistor. Since all of these elements are in parallel, I know that they all have the same voltage, so that first voltage column, you can go ahead and put 7.5 for each of them. The 10 amp current source are also pretty easy. You know that their currents are 10 amps and 5 amps. So now to find the current for the 2 ohm resistor. Well, that's Ohm's law. 7.5 divided by 2 is 3.75. And 7.5 divided by 6 is 1.25. Resistors always absorb power, so we don't even have to think about it. For the 2 ohm resistor, it's 7.5 times 3.75, which is 28.125 watts. For the 6 ohm resistor, it's 7.5 times 1.25, which is 9.375 watts. For the current sources, we got to go back to the circuit. So now, if we know at the top, I have 7.5 volts, and that's higher potential to lower potential, and the 5 amp current source goes in, the current goes in at the positive and out through the negative. The 5 amps is also absorbing power, and that's 37.5 watts. Now for the 10 amp current source, I have 7.5 volts is a higher potential than 0, so it's positive on top, negative on the bottom. The current goes into the negative and out of the positive, so that's negative 75 watts. Since the sum of the powers is 0, we have used KCL to show that this circuit does obey the law of conservation of energy. Now for the next example, we're going to use Kirchhoff's voltage law to confirm that the following circuit obeys the law of conservation of energy. How do I know I want to use KVL? Well, when you have a single loop circuit and all the elements are in series, we use KVL, where the first thing we do is define a clockwise current. This is an assumed direction. When we get to the end, if the numeric value for Ix is negative, we know that we assume the opposite of the correct current flow. The other thing we do is, since we know we always draw resistors to drop voltage, if I assume a clockwise current, Ix, the unknown current, then I can label the polarity on all the resistors, positive on the left, negative on the right for the 2 ohm at the top, positive on the top, negative on the bottom for the 12 ohm on the right, and positive on the right, negative on the left for the 4 ohm at the bottom, so that they're all drawn to obey the passive sign convention or to drop voltage. So the KVL equation would be the sum of the voltages around the loop is equal to 0. So I'm going to have negative the voltage for the 12 volt source, because that's going to be a rise, plus the voltage drop across the 2 ohm resistor, plus the voltage drop across the 12 ohm resistor, plus the voltage drop across the 4 ohm resistor, and that equals 0. It's a good equation, but not very helpful because I have 4 variables in one equation. It would be better to write the voltages in terms of my unknown current. And I can do this by using Ohm's law. So you have negative 12. Ohm's law states that the voltage drop across the 2 ohm resistor is 2 Ix, plus the voltage drop across the 12 ohm resistor is 12 Ix, plus the voltage drop across the 4 ohm resistor is 4 Ix, and that equals 0. One equation and one unknown, we can solve for Ix. Ix is equal to 2 over 3 amps. That's the missing piece of information we need to now confirm that this circuit obeys the law of conservation of energy. So let's make our power table. We have a column for the elements, the voltage, the current, and the power. We'll put the 12 volt source first, then the 2 ohm resistor, the 12 ohm resistor, and the 4 ohm resistor. They're all in series, so they all have the same current. 2/3, 2/3, 2/3, 2/3. The 12 volt source obviously has 12 volts across it, and because the current goes into the negative and out of the positive for that source, that's going to be delivering, so we write that as negative 8 watts. For the 2 ohm resistor, the voltage drop should be 2 times 2/3, or 4/3 volts. For the 12 ohm resistor, it should be 12 times 2/3, which is 8 volts. And for the 4 ohm resistor, it would be 4 times 2/3, which is 8/3 volts. Resistors always drop voltage and they always absorb power. So all of these would be absorbed. So I'm going to have 8/9 watts, 16/3 watts, and 16/9. When I sum the power for all of the elements, it does equal 0. So I have confirmed that this circuit obeys the law of conservation of energy. Now for the last example. We don't have a single loop or a single node pair. So for this example, I'm actually going to use a combination of KCL and KVL. So the first thing I'm going to do is to define some unknown values. We're looking for resistance. So if I can find the voltage across that resistor and the current through that resistor, I can use Ohm's law to get the resistance. So I'm going to label the voltage across the resistor Vx. I'm going to label the current through the resistor Ix. And then I'm going to write a KCL equation at this top right node. The KCL equation is going to be Ix, the current coming into the node, equals the current going out through the 24 ohm resistor plus the current going out through the 8 ohm resistor. Helpful, but not very. So a better way to write this would be that Ix is equal to the voltage across the 24 ohm resistor, which is 120, divided by the resistance, which is 24. That's Ohm's law, plus the voltage across the 8 ohm resistor. What is the voltage across the 8 ohm resistor? Well, remember, elements that are tied together on both sides, they share a single node pair, are said to be in parallel. Elements that are in parallel have the same voltage, which means the 8 ohm resistor also has 120 volts across it. So that's going to be 120/8. So Ix is equal to 20 amps. Now let's use KVL to find Vx. I'm going to do KVL around this loop on the left. So if we look at the 200 volt source, that's our voltage rise, -200, plus Vx, the voltage drop across the R resistor, or the unknown resistor, plus the voltage drop across the 24 and 8 ohm resistors, which is 120 volts, and that equals 0. So I have one equation and one unknown. So solving for Vx, Vx is equal to 80 volts. And now I can find R. Using Ohm's law, R is equal to Vx over Ix, which is 80/20, or 4 ohms. And how do we check our work? Well, the same way we've been doing all along. In order to check your work, we make a power table and confirm that this circuit obeys the law of conservation of energy. We'll do that now. So I'm making the column headings first: elements, voltage, current, and power. I now know that R is a 4 ohm resistor, so I'll put that one first. 4 ohms, 24 ohms, 8 ohms, and 200 volts. For the 4 ohm resistor, the voltage is 80 and the current is 20. Resistors always absorb power, so 1600 watts absorbed. For the 24 ohm resistor, that's 120 volts and the current is 5 amps, so that's 600 watts absorbed. For the 8 ohm resistor, the voltage is still 120, the current is 15, so that is 1800 watts absorbed. And the voltage source, the voltage is 200. It's in series. The 4 ohm resistor is in series with the 200 volt source, so they must have the same current, which means it's also 20 amps. Current goes from the negative to the positive, so that's -4,000 And finally, we sum the powers. And we see that it does add to 0, so our circuit obeys the law of conservation of energy, and we can assume our solution is correct. This concludes Lecture 2-1 on KVL and KCL.